So the new findings are pretty remarkable. Stanford researchers have shown that dialing down an overactive enzyme, LRRK2, can actually regrow lost cellular antennae in brain cells, which in turn revives dopamine signaling in a Parkinson's mouse model.
Yeah, that's fascinating. So, they used the LRRK2 blocking drug MLI2, right? And after a treatment period, these neuronal circuits, which were thought lost, started to come back?
Exactly. After about, 3 months of treatment with MLI2, the mice with the genetic mutation showed a full rebound in primary cilia, those antennas, and it essentially restored communication between dopamine neurons and the striatum.
Impressive. That's huge. It's almost like, rebooting a system where your phone regains service after having no signal. Suddenly, the messages, or in this case, the neuroprotective signals, are back.
Yeah, it's like the brain is getting its own upgrade. The primary cilia, which normally help cells send and receive signals, come back online, and then the cells start secreting those essential neuroprotective factors again.
Right. But I wonder, do you think these results in mice can directly translate to humans? After all, the human brain is a whole other ballgame.
Good point. The study did focus on a genetic form of Parkinson's, which accounts for about 25% of cases. The researchers hinted that because overactive LRRK2 isn't exclusive to that mutation, this approach might eventually help with other, more common
That's
forms.
promising. And it also seems like early intervention is key here, right? I mean, they mentioned that symptoms start way before the tremors show up.
Absolutely. The notion is that if patients are identified early, like long before the classic motor symptoms emerge, then inhibiting LRRK2 could not only slow the disease, but maybe even reverse some of the neuronal damage.
Right, early detection is critical. It's almost as if the treatment is buying the neurons a second lease on life by restoring their antennae and connectivity.
Exactly. And think about it. By restoring the ability of the neurons to talk to adjacent cells, specifically through sonic hedgehog signaling, it revives a whole network of protective measures. It's like, um, it's like finally getting all your lost emails back, reviving important conversations that keep the system running smoothly.
Yeah, that's a neat way to put it. But here's my concern. Given that the initial trial in mice took 3 months to show these astounding effects, isn't there a risk that by the time we diagnose Parkinson's in patients, too much damage might already be done?
It's a valid challenge. However, the study emphasizes that the earliest symptoms of Parkinson's, like loss of smell or sleep abnormalities, can appear up to 15 years before the tremors. So, ideally, with improved diagnostic methods, treatment could start early enough to make a real difference.
That does sound promising. And I guess it's encouraging to see multiple clinical trials underway with LRRK2 inhibitors. That could give us a broader picture of its potential across different Parkinson's types.
Yes, it's a turning point. If these findings hold up in human trials, it might reshape our approach to treating not only Parkinson's, but potentially even other neurodegenerative disorders.
Absolutely, it's an exciting development indeed. I'm looking forward to seeing how this research evolves in the coming years. Maybe one day, we'll really have a therapy that not only stops, but actually reverses neural degeneration.
That's the hope, right? There's still a lot to explore, but this breakthrough gives a real glimpse of potential.
Yeah, definitely.